اوكي قبل ما المحاضرة يجي ريكورد كل تمام دي ريكورد كنو باشي السر موديل يعني. Okay, so today's lecture we will study the electrical design of overhead lines. Generally, electrical parameters of overhead lines, we have three parameters. We have either resistance or inductance or capacitance. So we have to understand how to calculate each one of them and in order to be able to design an optimized system. First, line resistance of a transmission line is calculated by R equals to rho L over A. You already know that L is the length of inductance, rho is the resistivity of the conductor material, and A is the cross-section area of the conductor. So when we want to calculate the resistance of a transmission line, we will use this equation. In the resistance, we have something very important, we call it skin effect. Whenever we have overhead transmission lines, whenever we have transmission line conductors, we will have something we call it skin effect. Now, the definition of skin effect, or the reason we have skin effect, is because the alternating current is concentrating near the surface of the conductor material, as you can see from this graph. These pluses are the concentration of AC currents near the surface. Because of the skin effect, the cross-section area of the conductor is reduced, because in this side, as you can see, where we have pluses, the current is not flowing. So the cross-section area of the conductor material is reduced. What are the reasons that we have skin effect? So you have to know the definition, and you have to know what are the reasons, or what are the points that affecting the skin effect. First, nature of the material. Nature of the material. Diameter of the wire. If we increase the diameter of the wire, then the skin effect will be increased. Frequency. Skin effect increases with the increase in frequency and shape of the wire. Okay, less than 50 hertz, if we have frequency less than 50 hertz and a diameter, conductor diameter less than 1 centimeter, we can neglect the skin effect. We can neglect the skin effect. Now, this was the resistance of transmission lines. What about inductance of overhead transmission line? When we come to calculate the inductance of overhead transmission line, the process is more complicated than that of calculating the resistance. First, if we have a single conductor, how we will calculate the value of inductance or the value of the flux? In single conductor, we have two types of inductance, or we have two types of the flux. First one is the flux linkage outside the conductor. It means that we have a flux going from the center point of the conductor to infinity. Okay, to infinity. Again, we have a flux effect due to the outside of the conductor, and this flux is going from R, or from the radius of the conductor, towards infinity. This is flux linkage, outside flux linkage of the conductor. Final equation for it is Lx equals to 2 times 10 to the power minus 7 integration from radius, as we said, from radius to infinity, 1 over x dx. This is psi, okay? So this was the first inductance. Now, the other part, or the second type of the flux in single conductor, is the flux linkage within the conductor. Flux linkage within the inside of the conductor, okay? So this flux is going from the point R, or from the center of the conductor, until it reaches the surface of the conductor. When we want to find this value, we will finally come to the equation here. 2 times 10 minus 7 multiplied by 0.25 plus ln d over r, okay? D over r. R here is the radius, d is this value, okay? This is d, the distance between the center point of the inductor to the current density, okay? So now this was for single conductor. Remember, in single conductor we have two types of flux. One of them due to the internal currents inside the inductor, and it's going from the center of the inductor to the surface of the inductor. The other one is the outside flux, which is going from the center of the inductor to infinity. What about if we have two wire, single phase? We have two wires here. If we have two wires, the story is different. First, and most of the times, the diameter of two wires is equal. It means that radius of conductor A equals to radius of conductor B, okay? And this is the distance. So here we will have the effect of flux on conductor A by the currents of conductor A, and the flux affected by the current of conductor B. Now, the equation to calculate the total inductance, which is L1 plus L2, equals to 4, here, this equation, 4 times 10 to the power minus 7 ln d over r dash. R dash here is 0.7788 R1. Remember, you have to memorize this value. So R dash is 0.7788 R1. This is if we have single phase two conductors, okay? What if we have multiple conductors? Here, if we have multiple conductors, we will have different distances. Distance from conductor A to conductor B, distance from conductor A to conductor C. A current effect of conductor A will affect conductor B, will affect conductor D. So here in this type, we will use this equation, okay? 2 multiplied by 10 to minus 7, all multiplied by current of conductor A, ln 1 over R1 dash. Remember, R1 dash is 0.7788 multiplied by R1, radius of conductor 1. Here we assume that all diameters are equal. So this flux in conductor A is affected by the current through conductor A, also affects by current of conductor B, conductor D, and so on. In three-phase overhead lines, in three-phase we have two types of calculation. Either we have symmetrical conductors. In symmetrical conductors or in symmetrical spacings, we mean that the distance between conductors is equal. In other words, we mean that D1 equals to D2 and equals to D3. Okay, participants. داود تلقى المي داود سليمان داود دلفين.
نعم أستاذ.
اوكي هسه نسجل داود غايب. ديلما صباح.
بله سيدة.
وش بسيارني لأني واضحة.
يو واضحة سيدة.
اوكي هيلين عامر.
بله.
واضحة. داود سليمان نهات منا داودي غايبة.
بله سيدة بله عزيمة موجودة.
اوكي كمال ما عندك سؤال؟ واضحة؟
واضح أستاذ.
دافيريا واضحة. منو عنده سؤال؟
أستاذ
نعم.
طب بس القوانين يعني هواية والله، يعني شلون تكون علينا لو
لا
مثلا
طبعا.
تطلعنا بالامتحان؟
طبعا لازم تحفظ القوانين من تجي تلخص لك القوانين أو تكتب لك القوانين بورقة. قوانين جدا بسيطة ومفهومة، يعني مو كلش صعبة. قوانين سهلة.
أستاذ بس كثيرة يعني عما تحفظوها حتى تنسلخ.
مو هي لازم شو نسوي؟ لازم لازم تعرف هاي القوانين. بلي يونس نصرت. يونس ليش بسيار هنا؟ كي دي شو بسيارك هيا؟ اوكي ام غيابات تسجيل كن. هر ايكي نافي خواب مسج اگه فريقنا چات باشا. Okay, now let's continue. Please, at any time, if you have questions, just ask. In three-phase, we said either we have symmetrical spacing or we will have asymmetrical spacing. In symmetrical spacing, we mean that for three-phase, three conductors, D1 will equals to D2 and will equals to D3. This means whenever you have a symmetrical three-phase, means that current of conductor A plus current of conductor C plus current of conductor B will equals to 0. Okay, so here D1 equals to D2 equals to D3. Now the equation will be inductive of conductor A, of course, will equals to inductive of conductor B, and C equals to 2 times 10 to minus 7 ln D over R dash, okay? R dash. R dash here is 0.7788 and R B equals to RA and equals to RC, okay? D is either D1, D2 or D3 because the system is symmetrical, okay? Now, if we have asymmetrical spacing, whenever we have asymmetrical spacing, we will have problems in the transmission line. Who knows what is the main issue of having asymmetrical system? Sure. What is the issue of having asymmetrical spacing?
بلى سيدة.
What is the issue of having asymmetrical spacing in transmission line conductors?
خد زو دكتور.
Okay. Farhang,
بلى سيدة.
do you know the answer to the question? What is
لا
the
والله.
main
لا
issue?
سيدة نظرا.
Zana Sleiman.
بله سيدا ما ندي امبالانس چه بد بوما کو فیزید ما دي امبالانس بحكا انسيمتريكال بد
Okay, unbalance دي چه يعني unbalance is affecting what if we have unbalanced system?
سيدا بيجا حكا مع امبالانس ام هبد بيجا افكت بالسروان محاولات شيء ما كو درساي شونا كان احتمالا بدا اجريكو شكاركتنا وانش
No, if we have asymmetrical spacing, we will have different voltage drops. Different voltage drops. Okay. What is the solution? What is the solution to avoid the asymmetrical spacing? What is the solution to avoid asymmetrical spacing? The solution is something we call transposition. Transposition means that for every known distance, we will exchange the location of conductors, okay? Every known distance, we will exchange the locations of the conductors. This is called transposition. In transposition, we will fix the problem of asymmetrical spacing, okay? In order to avoid unbalanced system. Now, in asymmetrical spacing, we will have average inductance. The average inductance is 2 times 10 minus 7 ln cubic root of d1, d2, d3 over r dash. Remember, always the diameter of conductors are equal, but the distance between two conductors is different, okay? So this is the equation. Now we have something we called GMD, or geometrical mean distance. Again, using geometrical mean distance, we will calculate the inductance of transmission line. GMD is the other method of calculating the inductance. So in exam, if I ask you to use geometrical mean distance and you use the other method, then you will not get any score for it. So you have to know both of them. Okay, GMD mainly is used for transmission lines with double lines with more than 3 conductors. Okay, because if we have more conductors, then the previous calculations will be very difficult and not accurate. Okay, so in GMD, if we have a single phase line, okay, if we have a single phase line, we have this equation: 2 times 10 minus 7 ln d over r dash. In single phase line, almost is the same equation. Or we will have dm over ds. dm equals to d, which is the spacing between conductors, and ds equals to r dash, which is 0.7788 r. Okay, if we have, this is if we have single phase line. Okay, what if we have a single circuit with 3 phase line? Means we have line A, line B, and line C. Okay, we will have this equation again, same equation, but dm is changing. dm is cubic root of d1, d2, and d3, and ds always equals to r dash. Until now, everything is pretty much the same, but if we have double circuit 3-phase line, like this one, this is a 3-phase line with double circuit. We have circuit 1 and we have circuit 2. So here, the inductance or the current flowing through conductor A will affect conductor C, conductor B, conductor B dash, and so on. Okay, so we will have different inductance. In these types of circuits, we have to use GMD approach because GMD will make it easier to calculate the value of inductance here. Now, the main equation to find the equivalent inductance is 2 times 10 minus 7 ln dm over ds. Now, what is dm and what is ds? ds is cubic root ds1, ds2, ds3. dm is cubic root dab, dbc, dca. Okay. ds is called self GMD, okay? Self GMD, which is for each one of them 0.7788 R, okay? Now, DS1 is in conductor A. DS1, we will use this equation, is D from A to A, from A to A dash to A, and A dash, okay? And this is called self GMD, okay? Self GMD. And for B is B to B, B to B dash, B dash to B, and B dash to B dash. In C, again, is from conductor C to conductor C, conductor C to C dash to C, and C dash to C dash. If you just understand how to draw, you don't have to memorize the equation. It's going to be easy. This is called self GMD. Okay, this is called self GMD. Now the equivalent self GMD, it means for all the system, is DS. is ds, which will equals to ds1, ds2, ds3 under the cubic root. Now we found ds. Then we will have to calculate the value of dm. We have to calculate the value of dm, or mutual geometric mean distance. Okay, so you'll have DAB, DBC, DCA. Okay, DAB. So DAB is DAB dash, DAB again, DA to B dash, DA to B, DA dash to B, DA dash to B dash. So if you just understand the graph, you don't have to memorize. Look, DA to B is DAB, then DA to B dash, DA to B dash, then DA dash to B, DA dash to B dash. Okay? Then we will have B to C, which is B to C, B to C dash, okay, B to C dash, and then B dash to C, and B dash to C dash. It's very easy. Then the equivalent GMD will equals to DAB, BC, CA under the cubic root. Any questions? Is it clear? Do you have any questions? Okay, this is about calculating the inductance of a transmission line. What about the capacitance? Don't forget, always you have to know how to drive the equation. لازم اشتقاق معادلة جي تجبركي. لازم تعرف اشتقاق المعادلات. For single inductance, for double, for single phase two wire inductance, for three phase symmetrical and unsymmetrical systems, you have to know how to drive the equations for calculating the inductance. Now we have taken the resistance and the inductance, and the final parameter is the capacitance. Okay, is
أستاذ
the capacitance. نعم.
بس تقدر تكبر الشاشة شوية؟
شاشة مو واضحة هسه.
كلش نظمة.
هسه
إيه تمام.
okay. Now we will take the capacitance. Whenever we want to calculate the capacitance, we have to know the electrical potential, or the potential on a charged conductor. So the electrical intensity of any conductor is QA over 2 pi x epsilon. Okay, QA here is the charge per meter length, and epsilon is the permittivity of free space, is constant. X is distance from the center of the conductor to a point P, okay? To a point P. Now, to calculate the capacitance, first we have a single phase, two wires line, okay? We have single phase, two wire line. Again, the diameter of each conductor is equals to the diameter of the other one, with a distance between conductor A and B, we call it D. So here we will have an induced, or we will have a capacitance. Okay, we will have a capacitance measured in farad per meter because we have a distance here. Now, the value of this capacitance is calculated using CAB equals to pi epsilon naught. Don't forget epsilon naught is the permittivity of the free space, which is a constant. Pi epsilon naught over ln d over r. D is the distance between conductor A to B, and r is the radius of conductor A or the radius of conductor B, because RA equals to RB. You have to know how to drive this one, okay? You have to know how to drive this one. What if we have a neutral? What if we have a neutral point? We have two conductors and a neutral point. We will have different capacitance. We will have capacitance from conductor A to N, which we call it CAN, and we will have capacitance from conductor B to N, which we call it CBN. Now, CAN equals to 2CAB, okay? And CBN also equals to 2CAB. We already know that CAN or CBN is pi epsilon naught over ln d over r. Multiplied by 2, we will get the value of capacitance from conductor A to N, or the value of capacitance from conductor B to N. This is if we have two conductors with neutral. What if we have, again, three-phase line? What if we have three-phase line? Again, either we will have symmetrical spacing, it means that D1 equals to D2 equals to D3, or we will have unsymmetrical. If we have symmetrical, it's easy to calculate. We will just use this equation, 2 pi epsilon naught over ln d over r, where d equals to d1 equals to d2 equals to d3, and r equals to ra and equals to rb and equals to rc. And remember, the value of this capacitance is measured in farad per meter. Also, you have to know how to drive these equations. If we have unsymmetrical spacing, again, what we call this method, the method of exchanging the distance of the conductors in unknown length or space. What we call it? Who knows? What is this method called?
Transposition.
Transposition. Don't forget. What is transposition? Don't forget what is the definition of transposition and why transposition is important in unsymmetrical spacing transmission line. So if we have unsymmetrical three-phase transmission line, we will use this equation, 2 pi epsilon naught over ln cubic root d1, d2, d3 over r, okay? We have d1, d2, and d3, and r equals to ra and equals to rb and equals to rc. You have to know how to drive this equation. Any questions? كيف بالسيارة هنا؟ Any questions? Any questions? Is it clear?
Yes, it's clear.
Yes, it's
Okay, now please solve these examples. These examples are homework for you. 1, 2, 3, and 5 here, 4, 5. We have 5 examples. Please solve these examples. They are very important. If you understand how to solve these examples, then you will understand all the lecture. Okay, again, this subject is chapter 9 in our reference book. في محاضرة chapterina هي reference أما. Okay, next lecture we will solve these examples.
بس عود تخليها بالموديل.
شلون؟
بس عود تخليها بالموديل.
ايه راح اخليها بالموديل. عندكم الريفرنس بوك؟
أنا ما عندي.
منو عنده الريفرنس بوك؟
عندي أستاذ.
اوكي. عندك كبي دي اف واحد لو كشابترات؟
شابترات والله.
تمام. راح احاول اخلي الريفرنس بوك همنا على الموديل. اوكي. الريفرنس بوك هذا ممكن السنة القادمة همنا بالمرحلة الرابعة هم يفيدكم. كتاب جدا التوضيح مالته زين، بس دائما بأخطاء، يعني بها هواية أخطاء. فحاولوا من تحلون الإكزامبلات وهاي تتأكدون، خاصة من تحلون الكويستشنز، الأسئلة بنهاية الكتاب اللي بس منطي الناتج النهائي بها هواية أخطاء. ف this lecture is in chapter 9 in our reference book. I will upload the reference book also on Moodle and this lecture.
بس استاذ شو اسم الكتاب؟
أخلي لك الكتاب كله على هو Power System Analysis. أخلي الكتاب على هو هذا الشابتر 9. راح أخلي الكتاب على الموديل. أوكي.
تمام.
هذا الشابتر 9 هو Principle of Power System Analysis. راح أخلي الكتاب اليوم على الموديل. Do you have any other questions?
أستاذ
نعم.
بس آخر اشتقاق مطلوب.
إيه اشتقاقات كلها مطلوبة.
تمام.
اشتقاقات كلها مطلوبة. هذا الموضوع أيضا داخل بالامتحان المتر. المحاضرة الجاية حنحل إكزامبلات. إذا أخذنا بس دقيقة هشام. إذا أخذنا غير موضوع ما راح يكون داخل. بلي هشام.
إذا موصلنا بتجلك أبى حسابي چهار چابتر داخل.
لا بالعكس نقلك هما موضوعي كي همي ريفيو نا نقلك.
سدا چینکی سدا ما گلک مال دیجیتی سدا سه چابتر داخل کردی. اگه تاوش که برای سه چابتر سه داده گلک باش بید.
أفرنا نقلك ما ده نقلك. امتحان دوی پیوه مانا
نه پیشم بال دیو دا سیدا.
از دی بری خود میدی اگر تشتک هبی بیش ما نبازی. از دی بری خود ما موضوعیت ما کاتشینه. گر من دید قالكن از دی گیم کم. گر من دید نقالكن از دی هیل موکی خو.
درست سیدا ممنون.
کسی چی بسیاری دی هنا؟
سيدا بس اگه تاكيم كر بزاني بو چونكو مسيروش تنه تنجي بو يعني درو جوني فنسن ناس ينجي
ما تفيقافي دست بيبكن محاضرة خو أو المفروض على يعني
ما ديتا متر ما دوس باش متر ماي
المفروض يعني محاضرة يعني مروف بخينة هكذا محاضرة مروف بخينة.
راز بيجي سيدا بزانيش مثلا يعني تظاني متر مشاوي اما تجاوب ندا شو خلاص تسعي نابي بجوش برنامج الجوب داين راستي